In this video I'm going to show you how to differentiate equations where the y term is not always explicitly defined. So if you look at equation number 1 here, you'll see that y is clearly defined in terms of some x function, meaning that the y variable is isolated on one side of the equation. And this is actually quite easy to differentiate because all you need to do is apply the power rule to get that the derivative is 4x cubed plus 6x plus 0. But what about this function? Well, y is not isolated in this form, but you can certainly try and isolate y with by taking x to this side and taking the square root. We get that if we try and isolate y is equal to 7 minus x squared divided by 3 with the whole thing square rooted. All I did was rearrange this equation to make it explicitly defined in y. But as you can see, this is a real pain to differentiate. And furthermore, if you're trying to find some y value for some value of x, this makes it a lot more painful than finding it through this. So, and before I start implicit differentiation, take a look at the third equation. No matter what you do to this equation, you cannot isolate y. If you try factoring it out, you still have a y term because there's a y squared over here. So in case number 3, implicit differentiation becomes imperative. So why don't we try differentiating this one first? I'll come back to this equation implicitly. So if we apply the derivative operator to the entire formula, 3y squared plus x squared equals 7, we can distribute the derivative to get that the derivative operator of 3y squared plus d over dx of x squared plus equals d over dx of 7. So we can do two things right off the bat here. The derivative of any constant is 0, so we can just write that in. And the derivative of x squared with respect to x is simply 2x. But the hard part now is differentiating 3y squared with respect to x. And this is where the chain rule becomes involved. Say we define 3y squared as some variable z. So we can call z equal to 3y squared. So now if we differentiate both sides with respect to x, we get that dz over dx is equal to d over dx of 3y squared. But this is not very helpful. All I've basically done is rewritten this. But we know from the chain rule that dz over dx will equal dy over dx times dz over dy. So now we need to find dz over dy, and we'll have our derivative for 3y squared, because z is equal to 3y squared. So if we differentiate z with respect to y, we get that dz over dz over dy is equal to 6y, because this is simply an application of the power rule. You bring the exponent down and reduce it by 1. That's pretty simple. So now if we multiply 6y by dy over dx, we get that the derivative of z, or if you want to write it in a form that mimics this, the derivative of 3y squared, it's going to be equal to 6y, because that's dz over dy, times dy over dx. So we can replace this with this because of the chain rule. So we get that 6y times dy over dx plus 2x is equal to 0. So now just isolating dy over dx gives us that dy over dx, the derivative of y with respect to x, is negative 2x over 6y or negative x over 3y. So that is our derivative. And you'll note that there is a y term in the derivative, but it's not all that important. It don't, if you want to, if this is uncomfortable to you, you can substitute this thing back into here. But that is a severe pain, so I will not do it. I'm going to go back to the equation I had here and try and differentiate that using implicit differentiation. Alright, I believe the formula I had was 3x squared y minus y squared is equal to 27. So how do we differentiate this? Well, we can apply the derivative operator to everything. We get that the derivative of just apply the derivative operator to everything. So the derivative of 3x squared y minus the derivative of y squared and the derivative of 27 with respect to x. So this we know how to do, and this we know how to do. This is simply 0 because the derivative of a constant is 0, and this we learned how to do in the previous question. If we call z equal to y squared, we can do all that chain rule stuff to get that the derivative is 2y times dy over dx. And truth be told, if you want a really simple way of performing implicit differentiation, all you have to do is derive the y term as you would an x term, like applying power rules or whatever you want, and then just multiply it by a dy over dx term. And it actually works for anything. So say if you had z is equal to y to the fourth, the derivative of y to the fourth with respect to x is 4y cubed times dy over dx. Because all you need to do is multiply this dy over dx term by the derivative of y. So anyway, we can see that d over dx of 3x squared y minus 2y times dy over dx will equal 0. So this now gets slightly complicated. You actually have to use the product rule to different, because there's an x term and there's a y term. So if we say that u is equal to 3x squared and v is equal to y, the derivative of y with respect to x will be u prime times v plus v prime times u. So if we derive u with respect to x, we get that du over dx is equal to 6x. Not very hard. If we derive v with respect to x, this gets a little, well, not that much more complicated. The derivative of y with respect to y is 1, and then we just need to multiply it by a dy over dx term. So we get that dv over dx is in fact dy over dx. So now let's plug it into this equation. Dy over dx is going to equal, let's see, u prime times v, so 6xy, plus v prime times u, plus 3x squared times dy over dx. So now let's plug this back into here, because what this dy over dx really means is the derivative of all of this. So we get that the derivative of this formula with respect to y is 6xy plus 3x squared times dy over dx minus 2y times dy over dx is equal to 0. So now if we want to isolate dy over dx, it's a matter of simple algebra. We take 6xy to this side, so we get dy over dx, and then I'm just factoring out dy over dx here to save time, 3x squared minus 2y is equal to negative 6xy. So then dy over dx is equal to negative 6xy, all divided by 3x squared minus 2y. So implicit differentiation can get complicated, and if you want to find the second derivative here, that is a real pain because you have to use the product rule here as well as the quotient rule. But in truth, if you want to differentiate just a simple term, all you have to do is differentiate y with respect to y. Meaning that just pretend you're just differentiating this normally. Like say you have y to the 5th, the derivative is 5y to the 4th. Just pretend you're differentiating it and then multiply by a dy over dx term. You can actually skip the chain rule step if you have a good intuition of how to do this, but showing the chain rule always helps to understand why exactly you can take this shortcut. So I hope this has been helpful to you, and don't hesitate to inbox us if you have a question. And thank you for watching.
So how we solve it is, if you appreciate, deliberately they have given you the lower limit as a constant and the upper limit as b, which means for different values of b you get a function of b finally. So consider b as a variable. If you consider given, so this is given that integral 1 to b fx dx is b minus 1 sin 3b plus 4, because this is the area. The problem again, because it is the area bound by y fx, so y equal to fx, x is equal to 1, x is equal to b, x is equal to 1, x is equal to b, and that area is given as this. So the area by definition is integral of fx dx 1 to b is b minus 1 sin 3b plus 4. That's fair. So which means that I have to remove this integral sign, and if you differentiate, you remove the integral sign. So what we do is we differentiate both sides with respect to b. So I'm not writing it again. Basically, I should write it in the next step, but just to save space, what I write del b, and this side also I write del b of this whole thing. But this is just a function in b, as it is a variable. This is a differentiation with respect to b, and this is the first function and this is the second function. B minus 1 is the first function. So b minus 1 differentiation is 1, and sin 3b plus 4 plus b minus 1, and 3b differentiation will be 3. 3b differentiation will be 3. And sin differentiation is cos 3b plus 4. Good. Which precisely means that del b of 1 to b fx dx. But what is del b of 1 to b fx dx? Will be fb, upper limit first. So fb into differentiation of b. So it is fb into differentiation of b with respect to del b is 1. And this is a constant. So it will become f1. If this is 1, then it will become f1 and then differentiation of 1. Differentiation of 1 is 0. So that vanishes. So 1 is equal to this expression. So that is fb. Basically that means I write it here. fb into 1 is basically fb. And fb is sin 3b plus 4 and b minus 1 3 cos 3b plus 4. See, if fb is this, replace b with x. So that means fx is
Yes.
sin 3x plus 4 plus x minus 1 into 3 into cos 3x plus 4. Which means if you see, this was the problem was posed as an area problem, but basically it is a differentiation of derivative to b form. That's it. Thank you. Let us try to find out y as 1. That is, we will differentiate it and get the value. So there is an implicit function given. x to the power 2x, then 2x to the power x power y minus 1 equal to 0. So let us try to understand one thing. That I need to differentiate it in any case, so I have to do the differentiation correctly. There are two parts here. The differentiation of these individually. So x to the power 2x is more complicated than x into x adjacent to that. So let z is equal to x to the power 2x. So the standard process is that log z will be 2x and then x. So if I differentiate, then 1 by z dz by dx is equal to, if we differentiate 2x is 2 into ln x plus 2x by 1 by x, that's 2. 2x and then ln x differentiation is 1 by x is 2. So it is 2 times, basically it is coming out to be 2 times 1 plus ln x. So this 2 came because of the power 2. We can see that if it is x to the power x, then this 2 will not be there, which means that I know that okay, so which means that basically ddx of x to the power 2x is z, that is x to the power 2x into 2 into 1 plus ln x. This is true. And similarly, ddx of x to the power x is, I can guess, only this 2 is coming because of this 2 in the power. So obviously, this x to the power x into 1 plus ln x is easy to guess this if you don't remember. It takes a few seconds to do it. Fine. Moreover, I want y has 1, means x is equal to 1. Putting x is equal to 1. So I have to find y. So I do that first. So that is the first step. Don't forget to do it. So put x is equal to 1. We put x is equal to 1. Then I start getting 1. 1 is 1 to the power 1. So I get 1 minus 2. 1. X to the power 1 is 1 to the power 1. What y? Minus 1. 0. So, what y is 0? What y is 0? So, we know that what y is 0 means y is 5 by 2. So, y is 5 by 2. Tan 5 by 2 is infinity, so 1 by infinity is 0. So, y equal to 5 by 2. So, that means x is equal to 1 means y1 basically. y1 means that y at x is equal to 1 is 5 by 2. So we just calculate the value of y1. We need, then we just clean this off. This we can, okay. We only need these two results to see the order. Now we start implicitly differentiating. We need y dash, so we start implicitly differentiating from here. So how do you write it? I start writing x to the power 2x differences I already have. So x to the power 2x 2 1 plus ln x minus I'm writing here. Now 2 is 2 and give a bracket. X to the power x difference is x to the power x 1 plus ln x, and then what y remains unchanged plus this 2 was out. X to the power x remains as it is unchanged. What y differentiation is minus cosec square y. So brackets don't forget. Cosec square y, and then dy by dx is y dash. Okay, what y minus cosec square y into y dash, and then this is 0. So I close my bracket. You get 0. Above. After this is in control. So y dash 1 is straight away substituted here. If you appreciate that these expressions are close to, we know that y1 is 5 by 2, means y at x is equal to 1 is 5 by 2.
So we will be getting these values very closely. If we take common here, I'll take x to the power x and then 1 plus ln x and 2. If I take common, then I get x to the power 2x and then 2 times x to the power x dot y. That is nothing but y. Y plus 1. Are you getting my point? If I expand this 2 and then take common. In any case, you can substitute these values. So y dash 1 is what you need. So y dash, you can find out from here itself. Substitute x is equal to 1 and again simplify. You don't need y value directly. You may not. You can substitute x is equal to 1 here itself and start doing it. So can you try it? I'll write it here. And this is part of the work. So 1, 2, log 1 is 0. So 1 into 2. This is all we do. I hope I'll write it for you. 1 into 2 into 1 plus 0. You want me to write like this? Yes. Will you be able to substitute? Just see 1 into 2 and log 1 is 0. Is 2. Is just 2. Minus 2 brackets is 1 and then log 1 is 0 again. So this is 1 into 1 into what? Y. So there where we get the value because cot y we again know that we already found out that cot y was 0. So 5/2. So this whole thing becomes 0. And then this is 1 into minus cosec square. So inside the bracket is only this y dash 1 into this is 1 is minus cosec square y. Y is no y is again y1 is 5/2 cosec 5/2. So cosec 5/2 sin 5/2 is 1. So cosec 5/2 is also 1. So this whole thing is 1 is minus 1 into y dash. So it is y dash 1 into minus 1 is equal to 0. So substitute x equal to 0. It doesn't take so much time really. Implies 2 plus 2. These 2 vanishes, this 2. So anyway, I'll give it. Y dash 1 is equal to 0. This becomes 1. This becomes 1. So y dash 1 will be minus 1. What's the answer?
Minus 1.
Minus 1 is the answer. Oh, I did it right.
So
Yeah.
no, but we can do without using log.
Without using log, we can do it.
Without using log.
The log, the whole
So,
sum.
yeah, take minus 1 that side and take x per x common.
X bar x common.
Yeah. So if you take
Much
minus 1 on this side, then you get 1.
1.
And then
Take x bar x as common.
yes, then
So
Yeah,
that will be
you
x
can
bar
do-
x into x bar x minus 2 into cot y.
correct.
Then you take x bar x, the common x bar x to the other side.
Yes, okay.
That will be 1 by x bar x in the RHS.
Yes, 1 by x to the power x. Yes.
Then it will be x bar x minus 2 cot y in the LHS.
Yes.
Take the x bar x in the LHS to the RHS.
So what you are with that circus, I agree. So with that circus, what you are avoiding is the differentiation of x to the power 2x. You are trying to write x to the power 2x as x to the power x also.
Yes.
Or you can substitute x to the power x as z also and do it. Instead of keeping x to the power x as a complicated expression, you can put x to the power x as z.
Yes.
Then it becomes z square and 2z cos y, which is much easier to handle. So you will be only getting dz by dx. And dz by dx you can substitute later. Are you getting my point? If you put x to the power x as z, then what will become?
Z square.
Z square minus 2z cot y minus 1 is equal to 0. There are many ways of doing it. So in general, in an implicit expression, we don't try to segregate. Your approach of segregation may work in this particular problem. Yes, just take it. I am accepting. It's acceptable. In this particular problem, it is easy, then why not do it? I agree. But generally, in an implicit problem, you may not able to segregate. If it is sine of x plus y kind of stuff, you will not able to segregate. Taking sine inverse will become more complicated. Which means that the practice of implicit differentiation has to be there. Because in this segregation that you are talking, in some other problem you may not be able to do it. In this you may have to do. In any case, the result is minus 1 is just fine, easy. Okay? So we can try it in different ways as well. Yes, fair. Thank you.
In the section on level curves, level surfaces, level sets, we used in a strong way the implicit function theorem, to know that at a point on a level set where the gradient of the defining function is not 0, the gradient vector of the defining function is not 0, that the level set was smooth and the tangent vectors were exactly those vectors that were perpendicular to the gradient vector. It should have been unclear why the theorem that we use there is called the implicit function theorem. We never actually see that there's something that's implicitly a function of something else. It is the implicit function theorem. It's just you use a part of it. It doesn't make that so clear. In this section of the book, we want to look at the implicit function theorem again, look at implicitly defined functions, and actually look at implicit differentiation. This is a topic you should remember that you did in Calculus 1, so in one variable calculus. If you had a level surface and you wanted to implicitly define, see that one variable was implicitly defined in terms of the other one, and then you'd have a single variable function, which is why you can handle it in single variable calculus. We'll actually start out with kind of a single variable example, and then with an eye towards the multivariable case, and then I'll state the theorem, and then we'll look at a more complicated example. So, implicit differentiation, well, a typical problem, so probably the easiest example that's still complicated enough to show you what's going on. Suppose I take the function of two variables, f of xy equals x squared plus y squared. So if you look at level sets of this, there'll be level curves, provided that you look at where the value of this is positive. We'll go ahead and fix that, consider the level curve where f is 1. That, i.e., the circle, given by x squared plus y squared equals 1. All right, and the question is, in what sense does this equation define y implicitly as a function of x, and if it does define y implicitly as a function of x, what's the derivative of y with respect to x? So those are the questions. So in what sense does x squared plus y squared is 1 define y as a function of x? And if it does define it as a function of x in some way, what is dy dx? So this is a multivariable function, the f of xy equals x squared plus y squared. This is an ordinary derivative, but since we want to look ahead to more variables, you could think, oh, what's the partial derivative of y with respect to x? That doesn't hurt if you think of it that way. If a function only depends on one variable, its partial derivative and its ordinary derivative are the same. Okay, so what's the problem here? Well, you should know that x squared plus y squared equals 1 is a circle of radius 1 centered at the origin, and this is not the graph of a function. Right? This is not the graph of a function. Why not? Well, what's usually said is it doesn't pass a vertical line test, which is just a graphical way of saying that for a given x value, there could be more than one y value. Like a vertical line here hits the graph twice. And the point is that means for that x value, there are two corresponding y values, but a function is supposed to give you back one y value. So this is not the graph of a function. So, oh no, this doesn't define y as a function of x. But we can almost solve this for y as a function of x. As you should know, if you put the x squared on the right, and take square roots, but put in a plus or minus, you get y is plus or minus 1 minus the square root of 1 minus x squared, which is why you get two y values sometimes, because of the plus or minus. So really, there are two functions here. Two functions. There's y is the positive square root of 1 minus x squared, and y equals negative the square root of 1 minus x squared. And of course, the graphs of those, with the plus one, you get the top half of the circle, including the endpoints. And that's the graph of a function. It passes a vertical line test. And then you get the bottom half, including these overlapping 2 points on the x-axis. And that's the graph of a function. Great. So what you can see immediately is that, oh, well, if you're near a point, so suppose you're near this point, well, then there's only one function that we're interested in that corresponds to this equation. So because y is positive here you would want to choose, oh, yeah, the function I care about is y equals the positive square root of 1 minus x squared. On the other hand, if your y coordinate were negative, then this equation implicitly defines y as a function of x, but it would be y is negative the square root of 1 minus x squared. So yes, this equation does not define y as a function of x globally, but if you also know that y is positive or y is negative, then this implicitly defines y as a function of x. On the top half, you would pick this function. On the bottom half, you would pick this function. Okay. What about the derivatives? Well, of course, we can calculate the derivatives of these functions, and I'm going to. Then I'm going to write them in a nice way so that we can see that you can actually get the derivative of y with respect to x in either case easily from this equation without ever having to solve explicitly for y. So I want to do that so that we can see the kind of formulas we're headed towards. So suppose y equals the square root of 1 minus x squared. There's one thing I should have said before I do this. Before I go on, I should have said that you should notice there's a problem at 2 points. There are 2 points where there's no hope of using this equation to implicitly define y as a function of x. Namely, this point and this point, the 2 points where y is 0. Because when y is 0, anywhere near here, well, there's no way to decide, oh, do you mean the top half or the bottom half? This equation doesn't implicitly define y as a function of x in a neighborhood of these points, because there's always going to be this top piece that comes down to it and this bottom piece that goes into it, and then it's not the graph of a function. So you kind of expect that there are some problem points, and we'll see why. All right. Meanwhile, so suppose y is the square root of 1 minus x squared, so that we're assuming y is greater than or equal to 0. In fact, we're going to want y is unequal to 0, but we'll see that in a second. Anyway, I mean, we don't want those blue points that I just indicated, but if you had this, well, this is 1 minus x squared to the 1/2, and its derivative, dy dx, is 1/2 times 1 minus x squared to the minus 1/2 times minus 2x. The 2's cancel. You're left with minus x, and then 1 minus x squared to the minus 1/2 is 1 over 1 minus x squared to the positive 1/2, which is 1 over the square root of 1 minus x squared. And if you want, that denominator is exactly the function we started with. We get minus x over y. Well, of course, you can't have y be 0 here, so we need for this to be strictly positive. So, which means we're not at one of the blue points I indicated on the x-axis. Suppose we're on the bottom half, though. So suppose y is negative the square root of 1 minus x squared. So that's negative 1 minus x squared to the 1/2. Well, of course, you're going to get negative the derivative. So then dy dx is, well, is going to be negative this. So we're going to get x over the square root of 1 minus x squared. But if we get tricky and put the minus sign back there and put 1 there, then that denominator with the minus is exactly y for this function. And once again, you get minus x over y. So if you're happy writing a formula for the derivative involving x and y instead of just x, then you can have one formula that works on the top half or the bottom half, but they don't work when y is 0, namely you get dy dx equals minus x over y. So this is the kind of thing we're after more generally. We would like to know when does an equation of the form some function of any number of variables equals a constant, when can we at least in theory solve for one of the variables in terms of the other variables, at least near certain points? We don't expect to have a global solution because maybe the graph doesn't pass a vertical line test. But if we're near a point, can we say that, yes, the given equation, at least in theory, so that can we say there exists a function so that y is that function of x near a point? And if there is such a function, can we find nice formulas for the derivatives in terms of all the variables, but without explicitly having to solve for y? Can we do it just using the initial equation, the initial kind of equation that's implicitly defining the function? This is what the implicit function theorem is for and what implicit differentiation means. So let me state the theorem. And now we'll have any number of variables. So the theorem, so the implicit function theorem. I won't prove this, but it's proved, or at least the proof is sketched. There's a very serious sketch of it in the more depth section. It's almost entirely the inverse function theorem. You'd be clever and set yourself up to use the inverse function theorem to prove the implicit function theorem. But, all right, so suppose that f, which is a function of, it's all right, f equals f of x1 through xn, is continuously differentiable on an open neighborhood of a point P. And that, well, we want that the gradient vector of f at P is not 0, which means one of the partial derivatives is not 0, and I want to specify that partial derivative, which one it is, on an open neighborhood of P, and that the partial derivative of f with respect to xi evaluated at P is not 0. So I'm picking a coordinate. The typical assumption is the gradient vector of f is not 0 at P, but that means one of the partial derivatives is not 0 at P, and I need to actually look at a coordinate where that happens. Then there exists an open neighborhood of P, a conceivably smaller one. And I'll give this one a name. Open neighborhood U of P, and a continuously differentiable function a function of the other x's, so not this one, and a function, so it's a little hard to write. I'll write g is g of x sub 1, and then you go out to, we want to leave out x sub I, so I'll go out to x sub I minus 1, then x sub I plus 1, and then go out to xn. So the point is, it's a function of all the other variables except xi, such that what? This is the big deal. Such that for all x, so x is an n-tuple of the x coordinates, it's in U, this open neighborhood of P, f of x equals f of P, so that all this says is that x is a point on the level set of f that passes through P. If and only if x sub I equals g of the other x variables. There's a furthermore, but before I say the furthermore, I want to explain maybe in more down-to-earth terms what this means. All this is saying is that as long as the partial derivative of f with respect to I is non-zero at P, then if you take this equation, that f of x, your function f of x equals this constant, whatever f of P is, that this equation implicitly defines xi in terms of the other variables. That because there is this function g, and it says that, yes, xi can be written as a function of the other variables under those conditions. So theoretically, you can solve for xi. In practice, we never find explicitly this function of g. That's why it's called the implicit function theorem, and why you differentiate implicitly. You actually never produce this function g. And I say this function, the g is unique, at least, so this is unique, there's only one. It really, any two, if you had another one, they'd have to agree on some possibly smaller open neighborhood of P, but so it's essentially unique. But the furthermore is how you differentiate. Furthermore, so now that g is a function of these independent variables, and we're saying xi equals g, we can ask for the partial derivative of xi with respect to xj, where j is not the same as I. So with respect to these other variables, so furthermore, for j unequal to I, so you pick some variable that's not x sub I, we'd like a formula for the derivative of g with respect to the x's, or so the derivative of xi with respect to the other variables. So it's the same as the partial derivative of g with respect to xj. And what we want is a formula in terms of f, because as I've said, we don't want to explicitly solve for g. And the formula is very nice. You get this minus sign, and you get the partial derivative of f with respect to xj, and it's divided by the partial derivative of f with respect to xi. Now, this could be somewhat hard to remember. In a sense, the proof might help you remember, but the proof is involved enough that it might be confusing. You get this from the chain rule, the multivariable chain rule. It's not terribly difficult. Actually, it's relatively easy from the chain rule, but there's a confusing, slightly confusing part. How can you remember this formula? Well, you should remember that you want partial derivatives of f. It's going to involve partials with respect to xi and xj. The minus sign, just try to remember. How do you remember which one goes in the numerator and which one goes in the denominator? You're dividing by the partial of f with respect to xi. This is the partial derivative that is, you're assuming is not 0 at p, so you know you can divide by it at p, but since f is continuously differentiable, if it's not, the partial derivatives are continuous. If it's not 0 at p, then it's not 0 in a small neighborhood of p, so that in some open neighborhood of p, this denominator is never 0, so you can always do this division. All right, this is kind of the real implicit function theorem. And I want to go back to the example of the circle and show that it gives us the formulas that we got, negative, or the formula, minus x over y. And then I want to do a more complicated example, and then that will be that. So let's return to our simple example of the circle of radius 1, centered at the origin. So let's go back to example. So come back to f of xy is x squared plus y squared. And we're looking at f of xy equals 1. And we'd like to know, so this is x squared plus y squared equals 1. And we would like to know where the implicit function theorem tells us that this implicitly defines y as a function of x, and at those points we'd like to have a formula for the partial derivative of y with respect to x, which is the same as the ordinary derivative, because y would be a function of just x. So we need the gradient vector of f. The gradient of f is 2x. Actually, if we're trying to solve it implicitly for y as a function of x, then all we want is the partial of f. It's true, we only want to do this at points where the gradient vector is non-zero. But if we've decided we don't want to solve for x in terms of y, we know we want to solve for y in terms of x, there's no reason to calculate the entire gradient vector. We just want to know that this partial derivative is not 0 at p, at the point where we want to do this. So the partial derivative of f with respect to y is 2y. And so this will be non-zero any place that y is non-zero. So this is unequal to 0 if y is unequal to 0. So that the implicit function theorem tells us that yes, at least near a point where y is not 0, a point on this level curve, where y is not 0, we can implicitly solve for y in terms of x because this partial derivative is not 0. Well, that's what we found before. As long as y wasn't 0, as long as we weren't at those 2 points on the x-axis, we could solve for y. If we knew whether y was positive or negative, which would be determined by what point we were at. Great. So yes, this means we can solve for y. So this tells us you can solve f of xy equals 1 implicitly, or you can solve it. In theory, you can solve it. And I'm saying you can solve implicitly, meaning you just tell yourself y is a function of x. You can solve implicitly for y in terms of x. So maybe I should say in theory instead of implicitly. If you actually do it, it's not implicit anymore. So you can solve for y in terms of, in theory, for y in terms of x near any point on the level curve. So it has to be on the level curve. But you need where y is unequal to 0. As I said, this is what we saw before. Great. And, okay, then what is dy dx? If we do let y be the function that's implicitly defined in terms of x, what's the same as the partial derivative of y with respect to x? And according to the formula I wrote before, this should be negative the partial derivative of f with respect to x over the partial derivative of f with respect to y. All right, that variable matches that one, and this one matches this one. So what do we get? You get negative the partial derivative of f with respect to x, 2x, partial derivative of f with respect to y, 2y. You can cancel the 2's. You get negative x over y, which is what we got before, or when we actually solved explicitly for y in terms of x, given that y was positive or negative. Notice that to actually calculate this derivative from this formula, you will need to be given not just the value of x, but also the value of y. That's a reflection of the fact that globally, you can't solve for y in terms of x. And so you can't just be given x, because that doesn't determine the y value, so it wouldn't determine the derivative. So you need to be given the xy pair. All right, let's look at a more complicated example, but really, if you understand the implicit function theorem in that easier example, you probably will have no trouble with it here. But let's look at one more complicated example. So, example. Show that near xyz equals 1, 0, e, the equation two z plus xy e to the y minus z ln of natural log of z over x equals e, show that that equation, well, there are three parts. A, implicitly defines x as a function of y and z. And you should calculate the partial derivative of x with respect to y and the partial derivative of x with respect to z. All right, so that's the first part. Second part, oh, we can say that, oh, it also implicitly defines y as a function of x and z, and find the partial derivatives. The partial derivative of y with respect to x and the partial derivative of y with respect to z. And C does not implicitly define z as a function of x and y. At least not as far as being able to use the implicit function theorem to conclude it. It's conceivable that while the hypotheses of the implicit function theorem aren't satisfied, that somehow you can solve for z here in terms of x and y. Conceivable. But we really mean here that the implicit function theorem doesn't tell us that we can. All right. Well, before we do these parts of the problem, I should say that notice that algebraically, you have essentially no hope of solving for any of these explicitly because of this x being here and here. There's no good way to solve for x in terms of y and z. Because there's a y here and up there, there's no good way to solve for y. And because there's a z there, there, and there, there's no easy way to solve for z in terms of x and y. But the implicit function theorem applies and tells us, will tell us that, oh yes, x in fact is a function of y and z near this point, and y is a function of x and z, so there exist functions. There's also one thing that you're not told to do in this problem, but you should probably do it anyway, if for no other reason than if you're taking a test and you're asked this kind of question and you check what I'm about to check and it doesn't work out, then you should raise your hand or write on a test, aha, you made a mistake, I don't have to do this problem. You should actually check at this point, right, we need to apply the implicit function theorem at a point that's on the level set in question. We need for this point to satisfy this equation. And while we're not explicitly told to do that, and it would be a trick question if it weren't true, it's a good thing to check anyway. So I'm going to check that. Do you really have to? Well, I suppose not. You should just assume that the question's written correctly, but it's easy to check. And seriously, if you're taking a test or even doing a homework problem and just want to make sure you've written it down correctly, the book's written it correctly, or the test has been composed correctly, you might want to check this. So our equation, so I'm going to let g, so I'm going to give our function a name, let g equal 2z plus xy e to the y, minus z ln natural log of z over x. All right. I'd like to look at g of the point that we're looking at, 1, 0, e, just to verify that that point is on the level set where this equals e. You plug that in. Z is e, so this is 2e. Y is 0, so this is plus 0 times, who cares what it's times, minus e times the natural log of e over 1. The natural log of e is 1, so we get 2e minus e. Yes, we get e. So yes, this point is on the level set where g equals e. All right, to apply the implicit function theorem, we need to know that the partial derivative that we're interested in, if we're trying to show one variable as a function of the others, we need to show the partial derivative of g with respect to that one variable is not 0 at the point. So that's going to be true, since we're trying. since you're told to solve for x in terms of y and z, it better be that the partial derivative of g with respect to x is not 0 at this point. It also better be, because of part b, it better be true that the partial derivative of g with respect to y at 1, 0e is not 0. And part c should mean that the partial derivative of g with respect to z is 0 at the point 1, 0e, so that we can't apply the implicit function theorem. But let's check these partial derivatives. Partial derivative of g with respect to x. All right, 0 here. With respect to x here, we get y e to the y. With respect to x here, oh, well, you could write this out. In fact, it would probably be nice to go ahead and have this throughout the problem. We can use properties of logs and write this as, this is the natural log of z minus the natural log of x. So we get minus z natural log of z plus z times the natural log of x. So that's a little easier to take the partial derivatives with respect to. Partial derivative with respect to x, we get a y e to the y, and then here you get a plus z over x. We want this, maybe I'll evaluate them all at the point in a minute. Nah, I'll go ahead and do it. So let me call this point P, just for notational ease. So if I evaluate this partial derivative at P, all right, that means I'm putting in x is 1, y is 0, and z is e. If y is 1, y is 0, so we get 0 plus z is e, x is 1, so we get e. Okay, so that's not 0. The partial derivative of g with respect to x at the point in question is not 0, so the implicit function theorem tells us, in fact, that this equation, it's not here, but the equation g equals e, so this function equals e, does implicitly define x as a function of y and z near this point. The partial of g with respect to y. All right, partial of g with respect to y. The x goes along from the right, but we need to do the power rule here, the product rule here. It's x times the first thing times the derivative of the second, plus x times the second thing times the derivative of the first, so we get this. And that's it. That's the only part that depends on y. You evaluate at p. Evaluate at p. So you plug in, again, y is 0, so that's 0. You get 1, and x is 1, so here you get 1. Again, this is not 0. So yes, we can solve the equation g of x, y, z equals e. We can solve it. I mean, we know there's a solution for y as a function of x and z near this point. So yes, the equation g of x, y, z equals e implicitly defines y as a function of x and z. And finally, I'll try to cram it in right here. The partial of g with respect to z is, all right, we get a 2. And then no z's. Here you need to do the product rule, so you get a minus. And then it's the first thing times the derivative of the second, plus the second thing times the derivative of the first. And then you also get a plus ln of x. If we evaluate at p, what do we get? Well, I've said we get 0, but let's see. You plug in, y doesn't appear in here anywhere, so that's irrelevant. X is 1, and z is e. So we get, all right, well, this is 1. Z is e, so we get 2 minus 1 plus 1. Right? This is 1. If z is e, this is 1. 2 minus 2. And then plus the ln of x, but x is 1. So plus the natural log of 1, but that's 0. So yes, we do get 0. So what does this tell us? It tells us we cannot use the implicit function theorem to say that the equation g of x, y, z equals e defines z implicitly as a function of y and z. So that's part C, that you can't do this, at least by applying the implicit function theorem. And parts A and B, we check. The corresponding partial derivatives, partial of g with respect to x is not 0 at that point. So yes, this equation implicitly defines x as a function of y and z. And this equation implicitly defines y as a function of x and z because the partial derivative of this is not y. It's not 0 at this point. And then we want the formulas for the partial derivatives, but those are easy. Let me write them. Maybe I'll just do the ones for part A, the ones for part B, or, well, no, I'll do both. So we want the partial derivative of x with respect to y. Our formula for this was that you get negative the partial derivative of, I wrote f before, but now our function is g, the partial derivative of g with respect to y divided by the partial derivative of g with respect to x, right? This is, right, when we're doing this part, this is the part where the partial derivative of g with respect to x is not 0, so it's all right for it to be in the denominator. You have the negative sign, you have the partial with respect to the other variable. Well, we calculated these partial derivatives over there, so now you can, without just plugging in p, so now you can just plug in what we calculated. If I can read it, we get xy e to the y, xy e to the y plus x e to the y. Put this minus sign floating out in front. So the partial derivative of g with respect to y we found was x times y times e to the y plus x times e to the y. And the partial derivative of g with respect to x was y e to the y plus z over x. Right, y e to the y plus z over x. So you get this for the partial of x with respect to y. What's the partial derivative of x with respect to z? Well, you just get negative. You get negative the partial derivative of g with respect to z, and it's divided by the same thing, the partial derivative of g with respect to x. So again, we get this negative sign. You get the same denominator. Minus sign. And then we have to read off our previous calculation, partial derivative of g with respect to x, which with respect to z, which was 2 minus 1 plus ln of z plus the ln of x. Did I read that correctly? 2 minus 1 plus ln of z plus ln of x. Right. So these are the formulas you get. Yes, they're unattractive, but they were easy. Right? We just had to calculate some partial derivatives and divide. We never solve for x explicitly in terms of y and z, and we can't. But if you're given a point x, y, and z that satisfies this equation, then you can plug those in here and calculate these partial derivatives. All right, let's finish part B. I want to keep this. In part B, we were solving for y in terms of x and z. We saw that we could do that because the partial derivative of g with respect to y is not 0 at the point in question. So the question is, what do we get for the partial derivative of y with respect to x and the partial derivative of y with respect to z? It's the same type of formula. You get negative the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. And now we're in the case where we're solving for y in terms of x and z, or thinking that we implicitly, so there is a function, there exists a function y, there exists a function g, so that y equals g of xz, And that means that we're using the implicit function theorem, so we're assuming the partial derivative of, when did I switch from, I didn't do it over there. Yes, our function is called g, not f. So let me change those to g's. And yeah, we know in this case, when we're saying y is implicitly defined in terms of x and z, that the partial of g with respect to y is not 0. So it's all right for it to be in the denominator, and then you just read off our partial derivative calculations with, so you get minus y e to the y plus z over x divided by the partial derivative of g with respect to y, which is x y e to the y plus x e to the y. And the partial derivative of y with respect to z minus partial derivative of g with respect to z divided by the partial derivative of g with respect to y, and that is negative. The partial of g with respect to z, this thing, so negative, we get 2 minus 1 plus the natural log of z plus the natural log of x, all divided by the same denominator we had up here, partial derivative of g with respect to y, x e to the y, xy e to the y plus x e to the y. Yeah, again, the formulas are not pretty, but you wouldn't succeed in solving for y explicitly in terms of x and z. So you should think of these as nice formulas because, yeah, they're a little ugly to calculate, but at least it's doable in a reasonably short amount of time. And again, your answers come out in terms of x, y, and z. You know, ideally, you could just take x and you're asserting that there exists, that y is a function of x and z. So in theory, if you just gave x and z, you could produce the y. Well, that's true. There is only one y that corresponds to that x and z near the point 1, 0, e. But because we can't explicitly solve for y as a function of x and z, given the x and z, it's usually kind of impossible. They'd have to be very special for you to produce the corresponding y value. So typically, you'd be given x, y, and z to plug into these, and then you plug them in, and you get what you get. That is the implicit function theorem and how you differentiate implicitly in multivariable calculus. It's a handy thing to do when you really can't solve explicitly for one variable in terms of the others.
Hi. Let us solve one ISC 1990 problem from mathematics. These problems are on slopes and curves. The question is, find the coordinates of the points on the curve y equal to x by 1 minus x square. The curve is given, the function is given, for which the slope dy by dx is 1. That's fine. Now we see that this y is in the u by v form. I mean, this becomes my u, this becomes my u, and this becomes my v, u by v form. So let us recall that d by dx, u by v, is v square, v into du by dx, minus u into dv by dx. So dy by dx can be written as 1 minus x square whole square, that is v. Then I substitute v, then differentiation of u, that is x, u is x, so it's 1 dx by dx, and then I write u as it is, and then dv by dx is minus 2x, so minus 2x. We just simplify this, we get there. Now after simplification, if we get this, then we have to find x for which dy by dx is 1, because they have asked the slope has to be 1 for which x. So this expression is equated to 1, and for quick calculation, instead of carrying x square as a baggage, what we do is we put x square is equal to z. This is z. X square is equal to z. So I write this equation as 1 plus z, 1 minus z whole square equal to 1, and then we cross multiply and simplify. So ultimately we see that here it is a simple quadratic equation, that is what we get, and we get the final quadratic equation as z square minus 3z is equal to 0. We shouldn't cancel z here because then we will lose a root. We have to always take common and realize that z into z minus 3 is equal to 0, or z is equal to 0, or z is equal to 3. These are the two solutions. Now z is x square, z is x square. So I write x square is equal to 0 or x square is equal to 3. So x is equal to 0, plus minus 0 doesn't make any sense, and x square is equal to 3 means plus minus root 3. And so we find the corresponding y with this x. Now for x is equal to 0, y is 0, no need for this to be done, and we also try to do it for y. Find the value of y for x is equal to root 3 and another value of y for x is equal to minus root 3. And so y root 3 means the value of y when x is equal to root 3. We just substitute these values and we see that it is root 3, 1 minus root 3 square is 3, x minus 1 by x square was the one function, and we get minus 3 root 3 by 2. And then y at x is equal to, this is x equal to minus root 3. We can write it like this, y minus root 3. That's the way it is written. So we substitute the value again, x minus 1 by x square, this value x is minus root 3. We simplify this and we get root 3 by 2. So the corresponding points are 0, 0, then root 3 minus root 3 by 2 and minus root 3 and root 3 by 2. And then these are the functions. These are the points which satisfy the functions, and these pairs 0, 0, root 3 minus root 3 by 2, and these are the points which we are searching. And here the slopes are slope in all cases 1, right? So that was what was asked in the ISC 90. Thank you. Hi, let us solve one ISC Mathematics 1988 problem which is on functions and dy by dx, a simple one where a function is given y, which is a function of x, is 3x minus 1 whole square and 2x minus 1 whole cube, and we have to find dy by dx at point and the points on the curve for which dy by dx is equal to 0, which means we differentiate this, get dy by dx, and find out that at what point of x this is 0. Now we recall that 1 minus a minus b to the power 3 is a cube minus 3a square b plus 3ab square minus b cube, just a binomial expansion. We know this very simply from school days. So here we can simplify this as 3x minus 1 whole square is 9x square, then 2 into 3x is 6x plus 1, and 2x minus 1 whole cube is 8x cube minus 3a square, then 3a minus 1. We just use this formula and simplify this. So ultimately if we write it in a sequence, then we should write x cube first, so 8x cube minus 3x square minus 2, and then dy by dx is 24x square minus 6x. We differentiate this 8, and then x cube differentiation is 3x square, so 8 into 3, 24x square, and x square differentiation is 2x, so 3 into 2 is 6x. So dy by dx is 2x square minus 6x. So at x is equal to 0, we substitute we first solve dy by dx is equal to this expression is equal to 0. So we can take 6, we can common, and we put 6, 4x minus 1x 0. Then we will be substituting the values after we solve the x. Now x is equal to 1/4 and we already have x is equal to 0. So these are the two values for which we get. Now corresponding y, we get y is 0 means at y equal to, y at x is equal to 0. So at x is equal to 0, we just substitute x values and we have the expression for y already. So we use this functions and simplify, we'll get 0. Okay, and we simplify this, then we get the value as 0. Then again y 1/4, here it is y 1/4 means y at x is equal to 1/4. We put x is equal to 1/4, 3 into x, so x is 1/4, so 3 into 1/4 minus 1 whole square, and we keep doing it. And so we try to simplify this and we just proceed with the fractions. We get minus 1 by 16. So the corresponding points are 0, 0, x is 0, y is 0, x0, y is 0, and x is equal to 1/4, and then y is minus 1 by 16. So these are the pair of points at which we needed the values, and that was the question, right? Thank you. Hi. Let us solve a ISC 1984 problem on mathematics. It's a simple problem where the function y, which is a function of x, has been given as x minus 1, 2x square minus 7x plus 5, and you have to find out dy by dx at x is equal to 2. That's the problem. Very simple one. Now before we proceed, we try to see that by chance if this can be simplified. These are the trick questions that are given in the exams, that if we can simplify it, we try to factorize it. We see that 2 into 5 is 10 and minus 7, so obviously it can be written as 5 and 2. So 2x square minus 7x plus 5 we write as, with 2 and 2 I can take common, so I write minus 2x first, and then 7x I write minus 5x first after that, and then minus 2x is first, minus 5x is after that, and then we see that this is minus 7. So we just proceed with the factorization, and x minus 1 and 2x minus 5 is what we get. Now we see that x minus 1 can cancel out, and it is 2x minus 5 to the power minus 1. So dy by dx is minus 1 into the same thing. If this is z, so z to the power minus 1 is minus 1 z to the power minus 2. So whatever is this, minus 1 into the same thing to the power minus 2. So we have minus 1, 2x minus 5 to the power minus 2 as 2x minus 5 to the power 2 in the winner, and again we have the differentiation of 2x, and differentiation of 2x will give me 2. Let us not forget that. So dy by dx at x is equal to 2, I just substitute the value and get as minus 2. So that is what was the question, that find the dy by dx at x is equal to 2, and that gives us the marks. It's a very simple one. Next, we have another question from ISC 1985, a simple one again, that is, if f of x, which is y, ultimately this fx is y, is x square plus 3 and x cube plus 2x, then find dy by dx at x is equal to 1. Now we can write dy by dx as again u by v form. We recall that d by dx u by v is v square v du by dx minus u dv by dx. We just substitute these values. So v is x cube plus 2x whole square, and then v is x cube plus 2x, and then du by dx is x square plus 3, and then x square plus 3 is u, and then d dx of v. We just substitute this and simplify, and we proceed with the simplification, which you have to do. It is done here. You can pause the video and then do it yourself, but ultimately only on you practice and do it, then you will get the confidence. It is a very simple simplification. You just simply proceed with the basic algebraic expressions, and we hit upon this value finally, minus x square plus 6, x square plus 1, x square plus 2 whole square. If you simplify it, you will get it. So there is nothing much to do, except you have to just do it correctly. So dy by dx at x is equal to 1, we substitute x is equal to 1 here. So we substitute x is 1, 1, 6, then x square is 1, then 1, then x square is again 1, then x square is 1 plus 2, then say 1 plus 2 whole square, right? And then minus 7 into 2, we'll just simplify and we'll get minus 14 by 9, and that's the answer for ISC 1985, one simple problem, right? Thank you.